Good day and welcome to another edition of Algebra 2 Notes with Miss Faust. Today we're going to start looking at logarithms. This is lesson 7.15.1 and our essential question is, what is a logarithm? My writing is kind of messy there. Logarithm, and why is it useful? So this is a whole new operation that you're learning. But I think by the end of the next few days, you'll understand why it's useful. But first, have you heard about the mathematician who's afraid of negative numbers? He will stop at nothing to avoid them. Okay, so this first little part is just a little intro to help you think about why we need logarithms. If you don't want to write this down, that's okay. But I just want you to think for a minute about the fact that 5 times 2 equals 10. So if you think about multiplication, if you wanted to get back an answer of 5 using these same numbers, you would do 10 divided by 2 because the inverse of multiplication is division. If you wanted to get back a 2, you would still do division and you do 10 divided by 5 equals 2. So these are kind of like fact families you might have done in elementary school. Addition and subtraction are inverse operations, multiplication and division are inverse operations. So that idea of inverse operations brings us to this problem. 5 squared is 25. So that's a problem with an exponent in it. And you also know that if you wanted to get back the 5, you would do the square root of 25. So roots give the base from the exponent problem. Now, the question though is, what if we wanted the 2 back? So you might think about that and you might think, well, could I do the 5th root of 25? So the 5th root of 25 would mean that you multiplied something 5 times and got back 25. But the thing that you'd multiply 5 times wouldn't be 2, because 2 to the 5th power doesn't equal 25. Right, so we actually don't have, roots will not work in this. They won't give you back the exponent. So what we need is we need our newest operation called a logarithm. So the logarithm gives you back the exponent. And the way we write a logarithm, and you'll get lots of practice with this, we write the word log, and then you write a 5, or whatever the base is, dropped underneath it. So we say log base 5 of 25. So when you do the log base 5 of 25, the answer is 2. So the answer gives you back the exponent. And that relationship between exponential equations and log equations is going to be the big focus of today's lesson. So when we start talking about exponents, the idea is we need 2 different operations in order to get back to the numbers we started with. So roots we already know, and now we're going to learn exponents. I'm sorry. Now we're going to learn logarithms. So the big idea here, and let me just move this a little bit so you can see it better, perhaps. Okay, so the big idea is that if you start with an exponential equation, you also have a corresponding logarithmic or logarithm equation. And today is going to be all about converting back and forth between those. So the exponential equation is b to the power of x equals a. And the corresponding logarithmic equation is log base b of a equals x. So what you want to notice there, this base becomes the base in your log equation. The answer from the exponential equation is what you take the log of. And then the exponent from the exponential equation is the answer in the log equation. So those relationships are always going to hold true, and today and the next assignment you'll practice going back and forth between those a lot. So a couple of these that come up a lot. So we have b to the x equals a, which means log base b of a equals x. So most of the time you'll actually see a base written, but occasionally in these you'll see just the word log of a equals x, or you'll see ln of a equals x. And those two both have hidden bases. Those are the most common ones used. So this one, just the word log, has a hidden base of 10. And the ln, or the natural log, has a hidden base of e. And e is that number that we talked about in our last lesson. Comes up a lot in compound interest problems. So the equivalent equation for this, because we know that there's this little 10 hidden down here. So if we were writing the exponential equation for this one, we would write 10 to the power of x equals a. This one has the little e hidden down there, so if we were writing the exponential equation for that, we'd write e to the x equals a. So let's do a little practice going back and forth between forms. Let me just get a new page set up real quick. Questions, notes. So if, for example, and I'm just going to write this at the top of every page, so I have that right in front of me, and I can use that when I'm doing these problems. So if we convert to log form, we're going to start with something like 2 to the 5th equals 32. And the log form of that would be log, the b is 2, the a is 32, equals, whoops, I don't know why I put an x there. I put an x there because there was an x there, but it should be a 5. So log base 2 of 32 equals 5. Similarly, if you add y to the x equals 5, to rewrite that, you would write log base y of 5 equals x. If you had 10 to the 4th, say, equals 10,000, if you were rewriting that in log form, you would write log. You don't have to write the 10. There's no base, that's assumed. Log 10,000 equals 4. Okay, so those are just some examples of how you go into log form. If we were going the other way, and this is when it's going to be most useful, because this is how we can use it to solve equations, is we can convert to exponential form. So if we had log base 2 of 128 equals 7, we can rewrite that as 2 to the power of 7 equals 128. If we had log base 10 of x equals 4, well, that we can rewrite as 10 to the 4th equals x. And the really useful thing then is we can actually find what 10 to the 4th is. 10 to the 4th is 10,000, so x would equal 10,000. Similarly, if you had log base 3 of y equals 240, no, sorry, log base 3 of y equals 5. To rewrite that, you would write 3 to the power of 5 equals y. Well, 3 to the power of 5 equals y, then again we can find y by doing 3 to the power of 5, which is 343. If you knew log base, shoot, sorry, I'm trying to think of one off the top of my head. Log base 4 of 1 over 256. Don't be scared of the fraction. Log base 4 of 1 over 256 equals a. and we want to find a. So we'd say 4 to the a equals 1 over 256. Then we take a look at this. Well, 1 over 256, we can rewrite 256 as a power of 4. That's 4 to the 4th. So 4 to the a equals 4 to the 4th, or 1 over 4 to the 4th. But 1 over 4 to the 4th is just 4 to the negative 4. And suddenly you can see that a is just negative 4. So if you have a log problem like this, in order to figure out the value it's equal to, you rewrite it as an exponent, and then you go through those steps to figure out the exponential form. So let's just do one more example with some of those, and then you will be good to go. It's hard to get used to at first, but once you get used to using logs and you're remembering that relationship, you'll find that they're pretty straightforward. So again, our relationship, I always start with that. So I've got it when I need it. Go ahead and write your notes and questions as we go. So in this case, we'll call this example, we'll just call it example 1. We're going to say f of x equals log base 2 of x. And what we want to do now is we want to find f of 64, f of 1024, and f of 1 over 16. So what you want to think about when you see this is you want to think about all of these as y values. And you want to think about all of these, oops, yellow you won't be able to see, as x values. So basically what we're going to do is we're going to set up some equations to find what the y is equal to. So f of 64, we're going to call that y, and we're going to say y equals log base 2 of 64. So then what we want to think about is we want to think about the exponential form of that. Well, if this is our log form, notice it's just like this, but with the number on the other side, right? The y is over here. So it does the same thing as this. We could even rewrite this just to make our lives easier. So it corresponds exactly to what we're looking at. So the base is 2, the exponent is y, and the answer is 64. So if you have your blue exponent table, that's a real quick way to find these. If you don't, you try some powers of 2 on your calculator, and you find the power of 2 that gives you 64. And you'll remember that from a couple lessons ago. We did that when we were doing the series, geometric series. So 2 to the, what is 64? I'm trying to look it up behind me. 2 to the 6th. So since 2 to the 6th is 64, y is 6, which means f of 64 is equal to 6. So I did that sort of in a circular pattern, but I didn't want to take up too much more space on my paper. So now we need f of 1024. So I say y equals log base 2. My x is 1024. So I think about rewriting this equation now as an exponential equation. And when I do that, I would get 2 to the y equals 1024. So just like before, I'm looking for a power of 2 that's equal to 1024. Look it up on your table if you need to. Try some powers of 2 on your calculator. It's got to be more than 6 because 2 to the 6th was 64, and it's actually 10. So y equals 10, which means f of 1024 is equal to 10. So helpful with these to have that exponent table out, helps us find the answers more quickly and easily. The last one that we want is f of 1 over 16. So we say y is log base 2 of 1 over 16. Again, don't be scared of fractions with these. The one thing that a fraction means is that your answer is going to be a negative number. So when we do this, we rewrite it as 2 to the y is 1 over 16. So 2 to the y is 1 over, so 16 is what power of 2? Well, 2 to the 4th is 16. We're close, right? We have 2 to the y and 1 over 2 to the 4th. Well, 1 over 2 to the 4th is the same as 2 to the negative 4. So y must equal negative 4. So f of 1/16 is negative 4. Okay, so I'm going to stop there for now. When you get to class next, I will show you how to do logs on the calculator, but it's really important to know how to do them using these exponential equivalents and going back and forth. Okay, thank you very much. Have a great day.